is just like example number 5, except it's a downhill skier, and it gives the approximate distance that the downhill skier skis after 10 seconds, while t seconds from 0 to 10. And they use the method from example 5, it says it right there, to sketch the graph of the derivative. So now what we have is we have all these values here. So what I need to do is I need to make a table of the derivatives. So to make the table of the derivatives, I picked a midpoint. So I'm going to say 0.5 is 1 point. And then to calculate that, I'm just going to take the difference. I'm going to take 3.3 minus 0 all over 1 minus 0. I'm just going to calculate the slope of those 2 points. Right? Now, that gives me 3.3. And then, so it says, what does the derivative represent? Well, what is the y value? The units. This goes back to your physics. What's the y value representing? Feet. What does the x value represent?
Second.
Time and seconds. So it's feet per second. So what does the derivative represent? What's feet per second?
The speed.
The speed. Velocity or speed, right?
Right?
Now, wait, we're not done. Now, so what you could do, it says, in what units would the derivative be measured? Feet per second. Can you guess an equation of the derivative by considering its graph? So now here's the trick. I've got to do a couple of these and see if I can make a graph of it. So now for the next one, what's the next midpoint? 1.5. So I'm going to write this over here. So my next one midpoint is 1.5, right? And you can't see it, but it's from 13.3 minus 3.3 all over 2 minus 1, right? So that gives me 10 over 1. So that's 10 feet per second. Now I do the next one. What's the midpoint between 2 and 3? 2.5. Then I'm going to take 29.9 and subtract 13.3 and divide it by 3 minus 2. So now it's going to be 16.6 feet per second.
Oh, and take the differences between those slopes.
Yeah, and then you
And
take
then
the
you give
differences.
Oh.
Now what you could do, which might be a little more helpful, is once you've completed that table, then what you do is you just plug it in your calculator. So I'm going to use my other calculator though.
Oh, and you can just do the dx dy function on your calculator, right?
Well, you could do it that way too, but they want a graph of the derivative. So to get a graph of the derivative, I've got to plug in my table of values. So let me show you what I mean by that. So I've got this table of values here. So what I could do is I can model that. I can make a graph by entering that stuff in. So if I go to list, I would enter in 0.5, 1.5, 2.5, and you would do all the midpoints. And then the next column I will put 3.3, 10, 16.6 is it? And then I would do the scatter plot.
Always warm-ish.
And I would do the scatter plot of that. turn that on, and then I would do zoom stat, which is the last one, I think, right? 9. And so those are the 3 points, and then I would do some sort of regression. So for time's sake, I'm not going to finish the table, but it says, guess what equation of the derivative by considering its graph. And so how much of an increase are we having from one point to the next? Maybe I have, let me check my notes. Maybe I have the whole table, because it would look better if I have the whole table. Because I really want you guys, which one is that, 29?
Yeah.
29. I do have the whole table. So let's enter in the whole table. So if I were to go through and crank through and do all this math, my table with the derivatives would be like this. I would have a table, actually I'll just put it up here on the screen instead of writing it down twice. So this is the table of values right here.
Oh my gosh.
Okay, so what I would do is I'm going to come back in here and edit all the, I'm going to enter all this stuff in, all right? So I've got 3.5, 4.5, 5.5, 6.5, 7.5, 8.5, 9.5. And then I'm going to come over here and 23.3, 30.0, 36.6, 43.2, 49.9, 56.6, and 63.2. Whoops, that last one's wrong. 63.2. Now somebody said, Mr. Adams, why don't we just find what the difference is? What do I add to 3.3 to get 10? 6.7, right? Now, what do I add to 10 to get 16.6?
I'm at 6.6.
6.6, right? Now what do I add to get this?
6.7.
6.7. What do I add to get this? 6.7. What do I add to get this? 6.6. So if you had to guess, it's probably like 0.6 repeating, right? So now let's look at the graph. Doesn't that look like a straight line? So what does this graph represent?
The derivative.
The derivative. So my rate of change appears to be constant. So what can I do to figure out what that graph is? Linreg, right? So I'm going to go to Calc, come down to Linreg, and I'm going to y-vars it, right? Because I want to save it as a function. Do I have anything in y1? We'll find out. So now when I look at the graph, boom.
Got 99 pounds, so that ain't wrong.
What?
Oh yeah, I forgot about that. So how could I simplify that if you guys wanted to simplify it?
6.65x.
Yeah, you could say 6.66 times x, or t. And that's the answer in the back of the book, right? Now do you understand how that works?
Yes.
Now,